Welcome to your channel that teaches you corporate English every Welcome to your channel that teaches you corporate English every day.
Welcome to this masterclass. In this session, I want to teach you how to understand Python from a business and learning method perspective, especially if you are starting from absolute zero and you have never written a single line of code in your life. I am not going to show any code on the screen because before code there must be mental structure. People who jump directly into syntax without first building structure normally quit. Not because Python is hard, but because they begin in the wrong order. When I teach Python to beginners, I do not begin by opening an editor. I begin by teaching the mental model of what programming actually is. Python is not a tool for coders. Python is a way of describing logic in a form a computer can execute. This is the correct mental sentence to hold. Asterisk. Programming is the act of translating human intention into machine executable steps. Asterisk, if you understand that. You understand what you're really learning. You are not learning Python buttons. You are learning how to tell a machine what to do, step by step. I want you to imagine a human assistant. If you want that assistant to book a flight, you do not say, do everything. You must give steps. Open the site, search this date, compare price, choose option, confirm, pay. Python is exactly that, except your assistant is a machine and the instructions must be complete, consistent, and unambiguous. This is the first principle of this masterclass. Python is structured thinking expressed in a formal language. Asterisk, Part 2. Why Python is used in the real world without showing code before learning Python? People often ask, but where is Python used? They ask this because they want to make sure they are not learning something that is only academic. In business reality, Python has extremely high adoption because it reduces cost, speed, and manual labor. To make this tangible, I will not list industries. I will show you how. Python changes money decisions inside companies. Imagine a company that receives 12,000 invoices per month in PDF and has 2 people manually typing amounts into a spreadsheet. If each person needs 5 minutes per invoice and earns 3 reals per month, you are spending more than 36 reals per year only in typing time. A simple Python automation that extracts that information automatically runs 24/7 and reduces that cost to near zero. That is not code magic. That is direct financial optimization powered by logic. Another example in marketing. A team that manually downloads Google Ads reports, filters them, builds CSVs, and sends to Slack every morning. This takes 40 minutes per day per analyst. When you multiply by 20 working days and an analyst cost of 5 reals, you burn more than 2 reals per month only in manual reporting time. A Python script that runs at 8 a.m. and sends the processed file reduces that to 0 effort. In corporate language, Python converts recurring task cost into one-time build cost. In retail, imagine an e-commerce store with 600 products, adjusting prices manually every 3 days based on competitor prices. If one employee spends 3 hours each cycle, you are spending more than 36 hours per month only on price adjustment. A Python routine that checks competitor APIs and suggests new prices transforms a repetitive activity into an automated decision system. That is not programming hobby. That is margin defense at scale. These examples matter because they answer the correct question. Python is not learned to code. Python is learned to replace recurring human actions with deterministic logic. Asterisk. Part 3. What makes Python specifically suitable for beginners without code when someone starts from zero? The greatest risk is frustration in the first hour. Most programming languages punish beginners with long syntax, strict formatting, and a lot of visual noise before any real outcome. Python is different because its visual structure is close to natural human thinking. When you express a step in Python, the line you write looks conceptually similar to how you would express the step in words. That is why Python is used not only by engineers, but also by analysts, researchers, accountants, marketers, and managers. The barrier to first contact is lower, so people stay long enough to actually understand logic. In education theory, that is called retention advantage. The tool that demands less pain at the start produces more people who survive the first phase. From a psychological perspective, Python rewards people early. This is important. The human brain continues only if it feels progress. Many languages force you to learn 40 technical rules before you produce anything visible. Python lets you see results with minimal steps, and that early proof of competence keeps learners inside the journey. This is not a technical reason. This is a behavioral reason, but it is the reason why. Python created more first-generation programmers in the last decade than any other language. Part 4. The correct order to study Python if you start at absolute zero people. Quit Python not because Python is hard, but because they start by touching the wrong element first. Instead of starting with logic, they start with environment, tools, editors, or libraries. That is like learning to drive a car by first studying traffic law, engine structure, and tire chemistry. The correct order is always mental model gives structure, gives syntax, gives application, never the opposite. The correct beginning is not open-eyed. The correct beginning is learn to think step by step before touching a keyboard. A proper study sequence for someone at level 0 looks like this. Understand what a computer can and cannot do. A computer does not assume, infer, or guess. It executes exactly what is defined. Understand the nature of sequential thinking. Every result is a product of a list of ordered instructions. Understand the idea of variables in memory without using code. Think of them like labeled boxes where values are temporarily stored. Understand conditions and decisions without code. If X, then do Y. Otherwise do Z. This is logic, not code syntax. Understand repetition as cost reduction. When you repeat a human action, that is time. When a machine repeats a defined action, that is automation. Only after these 5 conceptual understandings are stable should a beginner open a Python environment, because then, when they see syntax, they recognize the concept behind the syntax, and knowledge becomes mapped, not memorized. Most people do the reverse. They see syntax with no conceptual foundation and try to memorize instead of understand. Memorization fails. Structure survives. Asterisk, Part 5. How to build learning consistency without touching code every day. Learning Python is not about intensity. It is about repetition with increasing clarity. Most beginners try to study for hours in one weekend and then stop for 20 days. That pattern always produces failure. The brain does not store logic by marathon sessions. It stores logic by frequent short exposures. Even 25 minutes per day is more powerful than 3 hours once per week. This is because the brain consolidates patterns while you are not studying, not while you are studying. The daily touch maintains the pattern active, and the consolidation happens in the gap. The correct system for someone starting from zero is not long sessions. It is small, consistent contact with structured objectives each day. When learning Python, what grows is not your hands. It is your mental narrative about how instructions flow. That narrative is a muscle, and muscles grow with frequency, not with fireworks. Another mistake is emotional comparison. People look at someone who already works with Python and think, I am very far behind. That thinking is mathematically wrong. Experienced developers are not far ahead. They are only many repetitions ahead. Repetition is a solvable problem. Time solves it. The only unsolvable problem is quitting. Asterisk Part 6. Why understanding? Python matters even if you never write code professionally. Many professionals believe learning Python is only useful if they intend to become developers. That belief is false. In companies today, technical decisions are made in rooms that include people from finance, marketing, operations, legal, and strategy. Not only developers. The professional who understands Python logic, even without writing code, speaks with precision when discussing automation, cost reduction, data, and scalability. They participate in decisions instead of watching decisions. For example, when a manager without technical literacy hears, we can automate it with Python, They do not know if that means 2 hours or 2 months. But a manager who understands Python thinking can ask the right questions. Is the task deterministic? Do we have structured data? Is the workflow stable? Is the output rule-based? Those 4 questions alone separate feasible automations from fantasies. That is business power, not code power. Python is not just a language. It is a mental instrument for designing efficiency. Understanding it changes how you think about work, about scalability, about cost, about time, and about what should or should not be done manually in a company. Closing of the Lizoni want to close this session by reinforcing the one idea. It remains if you forget every other word. Python is not something you learn in order to code. Python is something you learn in order to think in procedures. And thinking in procedures is how value is built at scale. A person who never learned code solves problems by adding people. A person who understands logic solves problems by adding instructions. If you internalize that structure, you are already ahead of most people who tried to learn Python but started at the wrong end. End of the class.
Welcome to your channel that teaches you corporate English every day.
Imagine you need to build the back end of a web application. You want something that can handle many users at the same time, something fast, something that can respond in real time without waiting too much. That is the type of scenario where Node.js became extremely popular. Node.js is not a language. It is a runtime environment that allows you to run JavaScript outside the browser, usually on a server. The idea behind it is simple. It lets you create back-end logic using a language that was originally designed for the web. Front-end Node.js became popular because it is non-blocking and event-driven. This means it does not stop and wait for slow operations like reading a database or asking an external API instead. It continues running and sends the result back when it is ready. This makes Node.js very good for applications that need to handle thousands of requests per second without crashing or slowing down. When you start learning Node.js at a beginner level, the most important thing is to understand what it actually solves, not the syntax. Many students jump into code without knowing what problem Node solves, and then they end up confused. So let me make it simple. Node.js. It's mainly used when you want to build a server that responds to requests from a browser or other applications. For example, when someone clicks login, create account, view products, send message. The back-end logic that handles these actions could be written in Node, another important concept. Node.js runs on a single thread but uses asynchronous operations to avoid blocking. That is why it can be so efficient. In many traditional backends, if a task is slow, everything waits. In Node, everything continues and slow work finishes in the background. This is why companies that deal with chat, live dashboards, streaming, APIs, and microservices like to use Node when learning Node as a beginner. You must stop thinking like a front-end developer writing tiny pieces of UI logic and start thinking about how data travels. In Node, your mental focus changes from how to show something on screen to how to respond correctly when someone asks the server for information. You begin thinking about routes, requests, responses, and how to send data back in the correct format. Node.js is also known for being lightweight. Instead of frameworks with many rules, Node gives you the freedom to structure things however you want. This is good for flexibility, but it also means beginners can get lost if they do not learn the core concepts first. The core concepts are what a server is, what a request is, what a response is, what HTTP is doing under the surface, and why Node acts like a middle layer between the user and the data. Another thing that makes Node attractive is its huge ecosystem. Because so many developers use it, there are countless tools built on top of Node, but as you requested, I am not going to talk about those now. The goal here is only to understand Node itself as a foundation. Without understanding the fundamentals of Node, none of the tools built on top of it make sense. When thinking about Node.js, think in terms of responsibility. The backend has responsibilities like authentication, storing and reading data. applying business logic, validating input, protecting routes, and managing communication with other systems. Node is the environment where those responsibilities live. It is not about making a button look pretty. It's about deciding what should happen when the button sends a command to the server. Node also changed how teams work. Before Node, many projects used one language for front-end and another for back-end. With Node, teams can unify the stack and use the same base language concept across the application. Again, not the topic here, but it helps you understand why Node was a major shift in the industry. For beginners, the first mental shift is this. You are no longer writing code that runs inside the user's browser. Now you are writing code that lives on a machine elsewhere and waits for people to contact it. That remote machine is the server, and Node gives it the ability to listen and respond. You don't need to know advanced concepts to get started. You only need to be clear about the purpose. If I ask what is Node, the correct beginner answer is not a back-end language or something to build apps. The correct answer is Node is a runtime that allows JavaScript to run on the server to handle requests and responses efficiently. A reason Node is great for beginners is that it teaches you immediately about real-world back-end behavior latency, concurrency, input validation, security, error handling, and performance. These are back-end realities, not academic exercises. Learning Node trains your brain to think like someone building software for real users, not like someone solving school problems. When you start practicing Node after understanding the concepts, the first real task is usually to build a simple server that answers something when accessed. Not because the code is important, but because the exercise teaches the shape of communication between client and server. Every backend begins with that shape. Many beginners make one mistake. They think the hardest part of backend is writing code. It is not. The hardest part is designing logic that makes sense. Node gives you freedom, but freedom without understanding becomes chaos. That is why conceptual clarity comes before syntax. If you know what Node is doing and why, the code will naturally make sense later. You also need to understand the mental model of events. Node applications react to events. A user sent data, a file finished loading, a response arrived, a timer completed. Instead of executing everything line by line, Node reacts to events as they complete. That is why it is called event-driven. This event mindset is the key philosophical difference between Node and traditional blocking systems. Asterisk. When you build a backend with Node, the first thing the server needs is a way to know what someone is asking for. That is what a route represents. It is like a specific door that the user knocks on to request something. If a person wants to see products, they knock on one door. If they want to create an account, they knock on a different door. Each door has a specific purpose. After the server knows which door was knocked on, the second job is to decide how to answer. That answer might be information, a confirmation, an error, or something else. The important part is that Node does not decide randomly. It checks which door was used and then triggers the logic that belongs to that door. Think of a restaurant. The waiter comes to your table not with any random food, but based on what you asked. Routes work the same way. The server listens to the request and responds with the correct thing assigned to that type of request. Inside each route, Node can do 3 categories of work before sending a response. Understanding what the user asked for example. Are they asking for data or sending new information to save? Doing the necessary work behind the scenes that might include checking credentials, reading data, applying rules, or communicating with another service. Sending back a final conclusion, it could be okay. Here is the data, or you are not allowed, or this operation is complete. So the mental model is simple. A route is not code. A route is a rule that connects a specific kind of request to a specific kind of answer. People new to backend sometimes imagine everything as one big ball of logic. Node forces you to think in organized pieces. Each type of request belongs to a dedicated rule set. That is what keeps large systems clean. Even if there are hundreds of routes, each one exists for one clearly defined reason. In summary, a route is a defined entry point for a specific request. and the response is the server's chosen reaction. After finishing whatever must be done, that is the foundation of structure in Node. Once you understand that every backend is a collection of these logical doors and answers, you stop feeling lost. You start designing with intention.
Welcome to your channel that teaches you corporate English every day.
Imagine you just received a request from a real client. They want you to build a system from scratch, not a tutorial exercise, not a classroom example, but something that will actually be used. Before writing a single line of code, your first responsibility is to translate that request into structure. The mistake most developers make is opening an editor too early. Real software is not born inside the code editor. Real software is born in the mental model of how the system will live, grow, and be maintained. When you start a project properly, you do not ask, "What do I code first?" You ask, "What are the parts of this system and how will they talk to each other?" A project becomes stable when its structure is intentional. If you try to design structure later, after code already exists, you pay a much higher price. The first layer of thinking is about boundaries. A real project is never one thing. It is many responsibilities inside one system. You must separate those responsibilities before they mix into a tangle. For example, business rules should not live in the same place as raw database access. Handling an HTTP request should not be mixed with authentication logic. The separation is not for beauty. It is for survival. When separation exists, things can evolve independently. When everything is glued together, any change becomes dangerous. So how do you decide the structure? You start by asking, what are the core responsibilities of this system? In almost every backend project, you will have at least these categories of responsibility. Entry points where the system receives external requests, business logic rules, and decisions that define how things work, data access, reading, and writing information. Cross-cutting concerns things that apply everywhere, like authentication or logging. Utility supports small helpers not tied to one domain. Well-structured project. Let's make sure that each of those lives in its own place instead of blending together before creating folders or naming anything. You should simulate the flow in your head. If a user asks for X, where does that request land first? Where does the decision happen? Where is the data fetched? Where does it return from? Where is the rule enforced if something is not allowed? If you cannot answer that in plain English yet, you are not ready to create the code layout. The second layer of design is direction of dependency. Good architectures flow in one direction. High-level rules do not depend on low-level details. For example, the business logic should not depend on the database implementation. The database implementation should depend on the business logic needs. If you flip that, the system becomes fragile because any database change breaks everything above. The third layer is future-proofing. You do not design structure for the code you write today. You design for the code you will need to write 6 months from now. Will this feature grow? Will other features appear next to it? Will another developer read this file and understand it without you sitting next to them? Real architecture is not about satisfying your present comfort. It is about protecting your future from chaos. Most beginners think architectural thinking is advanced. In reality, it is the opposite. It is the foundation you need before writing even the simplest feature. Without structure, even small features corrupt the project over time. Once you have the responsibilities, the data flow, and the dependency direction clear, only then you move to folder organization. The folder tree is not the architecture. It is only the physical reflection of the architecture you already designed in your head. People who start by creating folders without mental clarity create meaningless folders. When you structure a real-world backend, you are not trying to make it look clean. You are making it maintainable, explainable, and expandable. A clean-looking project that cannot grow is worse than a messy one that has solid principles behind it. Before writing your first file, you should be able to say the sentence clearly. If someone asks the system for X, the request enters here, the logic runs here. The data is handled here, and the response is produced here. If you cannot explain that verbally, you are not ready to structure or code. Asterisk, once that mental map is solid, you begin translating it into a structure with physical separation. The goal is not to create folders for the sake of folders, but to reflect the logical separation of responsibilities in a visible and predictable way. A developer who opens the project should immediately understand where to place a new rule, where to update a feature, and where not to touch. In a real system, one of the most important decisions you make early is where the rules live. Business rules are the truth of the system. They define what is allowed, what is denied, what happens under specific conditions. These rules must not be scattered across random files. When a rule changes, you should know exactly where to go. And that file should not contain networking code, database calls, or presentation details mixed into it. Another important part of structure is defining an entry layer. The entry layer is simply the part of the system that receives external interaction. That could be a web request, a scheduled job, or a message from another system. That layer should not contain the business rules. It should only take the incoming request and pass it down to the correct logic unit. Think of the entry layer as the receptionist. It's not the decision maker. Then you design where the data lives, not physically in a database, but logically in your architecture. The system needs a dedicated area that is responsible for interacting with data storage. This prevents you from sprinkling data calls everywhere. If data interaction is centralized, changes in database technology or structure do not break the rest of the system. You also must think about repeated behavior across the project, authentication, validation, logging, error handling, and so on. These are not features. They are rules that support every feature. If you mix them randomly into features, you create repetition and inconsistency. A structured system isolates these cross-cutting concerns. They can be reused consistently without rewriting them many times. At this stage, you have structure without code. This is the right order. Structure must exist before syntax. Code is the implementation. The architecture is the intention. Once you begin coding, if you follow the boundaries you defined rather than inventing new logic on the fly, if you need to implement a new feature, you don't ask, where do I put this? The structure already answers that for you. That is the signal that you designed correctly. A common failure in real projects is allowing small exceptions. For example, a developer thinks, I will just do this quick shortcut here, or I will handle this rule directly where I need it because it's faster. Those exceptions are never temporary. They become permanent debt that slowly corrupts the architecture. A project rots not because of one big mistake, but because of dozens of micro-compromises. A structured project feels heavy and slow only at the beginning, but becomes faster over time. An unstructured project feels fast at the beginning and becomes painful and slow later. That is the price curve you must understand as a professional. If you are building something that will live, structure is not optional. Before finishing part 2 of this explanation, I want you to notice something important. Everything we've discussed so far has nothing to do with Node, Python, Java, or any specific tool. Good structure is language agnostic. You don't structure because of Node. You structure because systems need order to survive. In closing this segment, a real project is not a pile of code. It is a controlled system of responsibilities. Architecture is the act of deciding those responsibilities and organizing them, so the system can grow without breaking. If that is clear, then you are mentally prepared to move from abstract structure into the practical act of planning the actual layers and flows of a back-end project.
Welcome to your channel that teaches you corporate English every day.
Part 1. Opening of the JavaScript Masterclass in English. Consultant tone, no code in this session. I want to give you a clear understanding of JavaScript from the point of view of someone who participates in business decisions, not from the point of view of a programmer writing syntax. My goal here is to equip you with the mental model that executives, managers, strategists, and product owners need when they work with technical teams that build web products. You are not here to become a developer. You're here to understand the logic, use cases, and consequences of JavaScript, literacy inside a company. Let me start with the fundamental sentence that you must internalize. JavaScript is the language that gives behavior to the interface. It is what makes a product feel alive. HTML defines what is visible. CSS defines how it looks. JavaScript defines what it does when the user interacts. From a business perspective, this matters because every digital product is judged not by its existence, but by its interactivity and responsiveness. No user cares that a web page exists. Users care that it responds, validates, reacts, updates, connects, and executes actions. All of that execution layer is where JavaScript lives. When you click Add to Cart, and the cart updates without reloading the entire page, that is JavaScript. When a form checks your email in real time and shows a red warning before you submit, that is JavaScript. When a dashboard shows dynamic charts that animate with new data, that is JavaScript. When a modal opens, a price updates, a step loader appears. A filter refreshes, that is JavaScript. This is why every executive who manages digital experience must understand JavaScript conceptually, because it is the difference between a product that simply exists and a product that performs like a living system in. To position JavaScript correctly in your mental map, I want you to store this second sentence. Python dominates the world behind the interface. JavaScript dominates the world in front of the user. Python is the logic behind the curtain. Servers, automation, data processing. JavaScript is the logic on stage. What the human actually touches and sees. This is not a technical distinction. This is a decision distinction. If you are in a meeting discussing data automation, Python enters the conversation. If you are in a meeting discussing UX conversion, dashboard behavior, or digital interaction, JavaScript enters the conversation. Executives who fail to understand this separation speak to engineers using the wrong vocabulary, ask the wrong questions, and negotiate timelines with unrealistic expectations. Executives who understand the territory, even without coding, gain control of technical conversations because they reason inside the correct domain. That is the real reason you are learning this, not to write instructions, but to think in the right dimension when the conversation is about interactivity, not infrastructure. Asterisk. Part 2. Why JavaScript is strategically important for business no-code. Consultant tone when you sit in a meeting about a digital product, a checkout, a dashboard, a portal, an internal system. A mobile web app, the decisive metric is never does it open. The decisive metric is how fast does it react to the user's intention. Business value on the front end is not existence. It is responsiveness, clarity, and reduction of friction during interaction. JavaScript is the layer that manufactures that experience to understand its business importance. You must see JavaScript not as a programming language, but as the execution layer of user expectations. Modern users expect instant response, validation, animation, conditional behavior, updates without page reload, personalized UI states, and integrated data feedback. None of that happens through static HTML or CSS. All of that is delivered by JavaScript-based logic and frameworks. If Python replaces labor by automating back-office actions, JavaScript replaces friction by automating front-office interaction. Friction reduction is not a design preference, it is a commercial weapon. If your competitor's checkout feels faster, they will convert more orders per 100 visits. If your competitor's dashboard updates instantly, users will trust the product more. If your competitor's form prevents errors before submission, their support cost decreases. Those outcomes do not appear in code editors. They appear in the company's P&L. When a CEO asks why conversion dropped, the reason is often not price or traffic. It is front-end behavior, a slow validation, a delay in a step, a missing visual feedback. That is JavaScript territory. If you cannot see that dimension, you talk about the wrong root cause and make the wrong decisions, there is another. Strategic angle. JavaScript has become the standard language of the client layer across the entire web economy. It is not optional. The browser speaks JavaScript natively. It is the default. That means every feature that must run inside the user's screen depends directly or indirectly on JavaScript. For a business leader, ignoring JavaScript is like ignoring currency exchange when running an international company. You can operate blindly, but you are operating without literacy and a fundamental dependency. This is why top product managers, heads of marketing growth leads, CX directors and founders invest time to understand JavaScript conceptually. They do not want to type code. They want to hold correct mental models so they can approve or reject technical proposals with clarity. Challenge developers with the right constraints. Forecast timelines, realistically detect lies, overpromises, and naive assumptions. Translate user behavior into technical requirements. Negotiate features in business language without sounding ignorant. Person in the room who understands the mechanics of the interface controls the negotiation around what is possible, what is fast, what is expensive, and what is risky. That control often decides who leads the project and who merely follows it. Asterisk. Dito Pello ChatGPT. Part 3. The correct way to study JavaScript if you are not trying to become a developer. The mistake most non-technical professionals make is trying to learn JavaScript the way developers learn JavaScript. That approach fails because developers study with the intention of building, while decision makers must study with the intention of understanding and reasoning. Those are two completely different skill sets. If your goal is not to code professionally, you must not begin with syntax. Syntax is decoration. The substance is the mental architecture of front-end logic. Before one line of JavaScript ever makes sense, you must internalize what JavaScript is responsible for in the system and what problem it is solving. There is a correct sequence for business-oriented learning. Understand the boundary of JavaScript. What JS controls and what JS does not control. UI behavior, yes. Server logic, no, unless Node.js is involved. Understand the reasons for JavaScript. Usage not because this is how people build, but to reduce friction, to validate before errors, to update without full reload, to react to user intent in real time, to make interfaces feel trustworthy and alive. Understand the event-driven nature of JS. JavaScript does not act randomly. It acts when something happens. A click, a scroll, a change, a submit, a load, a time trigger. If you do not grasp the idea of events, syntax is meaningless. Understand conditional interaction logic. Interfaces do not just show things. They show A under condition X and hide B under condition Y. That is business logic translated to UX rules before it is translated to code. Only after those four conceptual pillars are stable. Touch syntax, because then syntax becomes labels for concepts. You already understand, not strange symbols to memorize. This allows you to read and understand JavaScript conversations without writing it. Asterisk. Part 4. When to choose JavaScript versus Python in a business decision and a technical. Leaders make one of two mistakes. Either they think Python and JavaScript are competitors, or they think it doesn't matter. Tech will decide. Both are wrong. Python is chosen when the business need is. Automation of repetitive internal tasks. Processing and cleaning large volumes of data. Building APIs and back-end logic analytics. AI, ML, and heavy computation. Integrating systems behind the interface. JavaScript is chosen when the business need is. Improving what the user sees and touches. Reducing friction during interaction, making an application stateful and reactive. Updating parts of the screen without full reload, making the interface feel instant. In modern CEO or director who understands this, distinction can say sentences like, this requirement is front-end dependent. JS timeline rules apply. This is a back-end automation. Evaluate in Python. Not UI, we are confusing. Interaction with computation, separate the layers. Do not fix a UI symptom with a back-end solution. Wrong tool domain. That sentence structure changes the outcome of entire roadmaps. A person with JavaScript. Literacy, even without coding, prevents wrong decisions before they burn budget, asterisk. Final closure of the JavaScript LESOS-SON, JavaScript, is not important because it is a language. It is important because it controls the moment of truth, the moment when the user interacts. Python automates the invisible. JavaScript controls the visible. Business value lives where users decide, not where systems think. That is why every serious professional who participates in product, marketing, operations, CX, or strategy must understand JavaScript. Conceptually, you do not need to code to lead technical conversations. This literacy does not make you a developer. It makes you a sharper decision maker in a digital world. End of the class.
Welcome to your channel that teaches you corporate English every day.
Part A, opening the C, C++ masterclass. Before we talk about C or C++, you must understand why this topic matters for someone in business, not in engineering. C and C++ are not just another language. They are the languages used when failure is expensive, when performance is non-negotiable, and when the software is close to the physical world hardware. Memory, devices, embedded systems, telecom, aerospace, automotive, medical equipment, banking core, etc. Closing parenthesis. The correct mindset is this: Python automates convenience. JavaScript controls interaction. C, C++ controls reality. C, C++ is chosen when a company cannot afford delays, cannot afford waste, and cannot afford abstraction overhead. It is the layer used in systems where timing, memory, and hardware behavior are mission critical, not optional, for a business professional. The reason to understand CI/C++ conceptually is simple. Whenever you are in a project where speed, determinism, safety, or hardware integration is a constraint, the engineering team will either use C, C++, or use something that runs on top of C, C++. That means C, C++ is not a developer preference. It is an architectural consequence. When people ask, why does this still exist if Python and JavaScript are easier? The answer is not historical inertia. The answer is physics and risk. Python is easy because it hides complexity. JavaScript is convenient because it lives in the browser. C, C++ is used when hiding complexity is too expensive, too risky, or physically impossible. You do not choose C, C++ because you like complexity. You choose it because the cost of abstraction is higher than the cost of control. In finance, this is called a risk trade-off. In software, it is exactly the same principle. C and C++ sit at the layer where computers stop being an idea and start being a machine. That is why these languages remain relevant decades later, because computation is physical, and anything that runs close to the metal must respect the laws of the machine, not the comfort of the developer. Part A, why C, C++ still exists in modern companies. The first thing you must internalize is this: C, C++ is not old technology. It is foundational technology. It is used today not because companies refuse to evolve, but because certain categories of problems never moved away from the physical constraints that C, C++ is built to handle. There are 4 business-level reasons why C, C++ is still actively chosen. 1. Performance is money in many industries. Speed is not a cosmetic detail. It is a cost function. If you run a high-frequency trading system that processes millions of events per second, a tiny delay means losing millions in missed execution. Python cannot give that deterministic speed. JavaScript cannot give that deterministic speed. C, C++ can. 2. Hardware is non-negotiably thing that runs on the device itself, not on the browser, not on the cloud, must speak to hardware directly. Sensors, chips, controllers, embedded boards, firmware, robotics, automotive exus, medical diagnostic devices, telecom routers, aviation systems. You cannot ask a pacemaker, a flight controller, or a vehicle brake system to wait for Python to interpret. In critical environments, the machine must execute instructions with zero ambiguity and maximum control. That is C++ territory. 3. Failure has legal and financial consequences. When a mobile app freezes, users get annoyed. When a C++ component inside an aircraft freezes, people die. When a Python script fails, you retry. When C code controlling a banking ledger fails, billions can move incorrectly. In high-risk sectors, aviation, defense, automotive systems, medical devices, banking cores, C++ is not a preference. It is risk mitigation for abstractions of hidden cost languages. Like Python and JavaScript are easier because they add layers between the code and the machine. Those layers are helpful until they become expensive. Every layer between you and the hardware consumes CPU, memory, electricity, and time. At small scale, this is irrelevant. At industrial scale, abstraction becomes a recurring operational cost. In long-running systems, banks, telecom, industrial automation, satellites, embedded devices that operate for 10+ years, abstraction is a financial liability. C++ eliminates that cost by removing layers. Bridge to the next part. Decision perspective. Understanding this changes how you talk in boardrooms. When engineers propose C++, they're not being old school. They're signaling that the constraints of the problem are physical, financial, or safety critical, not just logical. In the part 3, I will shift to how a business professional should speak about and govern decisions involving C++ without touching code. Part 3, how to speak about C++. In business discussions, without writing code, when C++ enters a conversation, the correct reaction from a non-technical leader is not to judge the language, but to recognize the nature of the constraint. You do not say, "Why not use something more modern?" You say, "What constraint makes low-level control required here?" That is the right question, because C++ appears only when one or more of these are true. Latency can't be tolerated, failure has cost or liability, memory must be managed explicitly. The code must live close to hardware. Abstraction overhead would accumulate in cost. A business-literate person does not repeat slogans like C++ is fast. They translate that into executive language. This solution demands strict control of time and memory that puts us in a C++ domain, since this process runs continuously and at scale. Abstraction cost is not acceptable. Low-level implementation is justified. Or because this component interacts with hardware and safety systems. We cannot rely on high-level interpreters. Notice, no syntax, but precise framing. That is what gives authority in a room full of engineers. Part 4. When to approve. Question or reject a C++ proposal at director. Or product owner with literacy does not simply accept or reject the proposal, they interrogate the constraint logic. You approve C++ when constraints are structural. The system is embedded in a device and must run deterministically. You question C++ when the constraint is assumed, not proven. Show me the performance or safety metric that eliminates high-level alternatives. You reject C++ when the team is using it for ego or habit. Not necessity. There is no critical constraint here. Use a maintainable high-level stack. Business literacy about C++ is not learning how to code it. It is learning when the risk, cost, or physics justify its use. Part 5. Final closure of this lesson. C and C++ are not old school. They are the languages chosen when physics, money, and liability outweigh developer comfort. Python simplifies work. JavaScript improves experience. C++ protects reality if you work in strategy, product, operations, finance, governance, or leadership. Your role is not to write these systems. Your role is to recognize when the problem itself demands this class of tools. You earn respect in technical rooms, not by coding, but by framing the decision correctly. If the risk is high, control is mandatory. If performance is contractual, abstraction is a liability. If the system touches hardware, low-level languages are not optional. That is why C and C++ are still here, not because the industry is slow, but because reality does not modernize just because syntax does. End of the class.
Welcome to your channel that teaches you corporate English every day.
Error 1. Starting to code before framing the boundary of the problem 1. Deep explanation backend. Projects don't fail because code is wrong, they fail because the starting conditions were wrong. When you begin coding without first declaring what the system is not responsible for, you create an open container where every new idea can later be inserted as if it were expected. From that moment, the project stops being finite and becomes evolutionary chaos. Code is not the problem, the absence of a boundary is. 2. Early detection signals. You can detect this mistake in the first week by listening for questions like, are we also doing feature X? Nobody knows. Architecture discussions happening before business intention stabilizes. Tasks being added without impact review. People saying we will see that later instead of making a decision now. 3. How to prevent correct you fix this before code exists. Write a non-goal. List explicit things the system will not do. Block new scope until cost and impact are explicitly approved. Align the business constraint. Before aligning technical design, treat uncertainty as a blocker, not as something to push into the future. For a realistic example, a bank starts an internal API layer for accounts. Halfway through, product asks, can you also expose loans and cards since it's already being built? Team says yes. Now the architecture must serve 3 domains instead of 1. The project doubles in complexity without doubling the budget. And now the blame will land on engineering, even though the root was boundary failure. 5. Financial operational consequence A. Backend without boundary never finishes, which means cost continues and trust declines. Projects like this don't die in code, they die in reputation and budget erosion. 6. How you explain this in a meeting. We are not failing because of code. We are failing because the system was allowed to include anything. Until we define what this project will not do, there is no such thing as done. Asterisk ERROR 2. Choosing architecture based on preference instead of constraints. 1. Deep explanation. You do not choose a backend stack because it is popular, elegant, or comfortable. You choose it because it survives the constraints. Architecture is not a personal preference. It is a response to business pressure, throughput, latency, SLA, regulatory conditions, lifecycle cost, and risk profile. When you pick architecture before defining constraints, you architect for a fantasy instead of reality. 2. Early detection signals. You can detect this mistake immediately when you hear, we always use this stack. This is what I like. Architecture was chosen before volume. SLA or compliance were even discussed. No document. Connects the stack to the expected constraints. 3. How to prevent collect constraints. First, traffic, durability, memory, security, cost to maintain. Force the architectural justification to reference constraints, not opinions. Require a second reviewer who was not part of the decision to break bias. Reject architecture proposals that cannot articulate. Cost of ownership. For realistic example, a startup builds a high-frequency pricing engine using Python because the team knows it. Later, they discover the execution must run under 10 milliseconds. The language was never chosen for that constraint. Now, they must rewrite under pressure instead of deciding correctly at the start. 5. Financial operational consequence. Wrong architecture causes rewrite cost, delays, SLA violations, and opportunity loss. You don't lose money because the code is bad, you lose because the chosen technology was misaligned with physics and risk. 6. How you explain this in a meeting. A stack is not a matter of taste. It must be justified by the constraints. If the constraints are not written, this architecture is a guess, not a decision. Asterisk ERROR3. No single source of truth for data. One deep explanation: back-end systems do not break only because of bugs. They break because different parts of the organization compete for authority over the same data. When more than one system believes it is the truth, you do not have a technical problem. You have a contradiction engineered into the architecture. From that point forward, every integration becomes a dispute of ownership instead of a flow of information. That is structural failure, not incidental failure. Too early detection signals: you can detect this before launch if you notice. Two teams say our system is the correct value. API responses differ for the same entity depending on where you call. People speak about fixing manually later. Instead of establishing rules, data conflicts are treated as bugs instead of design. Flaws 3. How to prevent correct. Designate one system as master for every critical field. Other systems must consume or cache, not co-own, for every conflict scenario. Declare a winner rule in advance. Reject deployments where ownership is ambiguous. For realistic example, an e-commerce platform treats both ERP and checkout as sources of stock truth. During a sale event, values desync. Clients get charged for items that don't exist. The problem is not availability. The problem is dual authority. 5. Financial operational consequence. Multi-master truth forces refunds, conciliation, incident time, and regulatory exposure. You don't lose money from the bug. You lose money from lack of governance of truth. 6. How do you explain this in a meeting? This is not a bug. This is a governance failure. Till we define a single system of record, every integration will break by design. Asterisk error for designing for delivery instead of designing for maintenance. 1. Deep explanation. Most leaders treat development as the cost and maintenance as an afterthought. In reality, development is the cheapest phase of a backend. It's expensive. Part is running, fixing, logging, securing, and evolving it across years. When you design only to ship, you build systems that are financially impossible to sustain once they are live. To early detection signals: no owner defined after release, no monitoring, no rollback plan, no observability baseline. PR is accepted because it works. It's not because it survives production. All trade-offs bias toward speed. Never longevity. 3. How to prevent correct. Ask, how will we support this for 3 years? Before, when can you deploy? Make logging alerts, rollback mandatory, not optional. Assign operational ownership before coding starts. Reject solutions that reduce build time, but multiply support time. For realistic example, a marketplace launches a payment service. Fast with zero observability. When incidents begin, engineers cannot diagnose root cause. Every hour of outage costs revenue, while the team is blind. Cost now exceeds the cost of building it properly in the first place. 5. Financial operational consequence. This mistake converts velocity into debt that compounds, not technical debt, but cash burn and reputational decay. 6. How you explain this in a meeting: shipping is not the cost. Running is the cost. If we design only for delivery, we are committing ourselves to an infinite operational burden. Asterisk error 5. Confusing speed with actual progress. 1. Deep explanation: a backend does not move forward just because code is produced quickly. Fast execution without alignment creates systems that run today and collapse tomorrow. Many teams are praised for shipping fast, when in reality, they are accumulating silent instability at high speed. Motion is not progress. It is only progress if it is in the right direction and under the right constraints. To early detection signals: you can see this mistake before the system fails by noticing. Demos focus on it runs instead of it is safe and repeatable. Business pressures override. Architectural reasoning, temporary shortcuts, become permanent without review. People treat velocity as success instead of risk acceleration. 3. How to prevent correct measure cost of consequences. Not only speed of delivery, require justification of direction before approval. Of execution block features built on top of unresolved ambiguity. It's normalized stopping development when alignment is missing. For a realistic example, a fintech rushes features to win investor timelines. 6 months later, auditing reveals inconsistencies across ledgers. Now the company must freeze roadmap to fix fundamentals. losing the exact speed advantage they thought they had. 5. Financial operational consequence speed without governance. Converts into expensive rework, regulatory exposure, loss of trust, and time lost correcting avoidable mistakes. 6. How you explain this in a meeting. We are moving fast in the wrong direction. That is not acceleration. That is structured failure with a shorter runway. Asterisk final closure, spoken style conclusion in English backend. Projects do not collapse because one engineer made a typo. They collapse because the project was born with the wrong logic of governance. If you start without boundaries, if you choose architecture without constraints, if truth has no owner, if you design for launch instead of for life, and if you confuse speed with progress, the failure is not a surprise. It is scheduled. You prevent back-end disasters not by hiring better developers, but by making better decisions before development exists. A strong back-end is not the result of good code. It is the result of correct thinking before code is allowed to begin. That is what senior people understand, and juniors don't. End of the master lesson.
Welcome to your channel that teaches you corporate English every day.
Section 1. Early failure in coded indecisions. Not in code and back-end projects. Failure does not begin at the moment of a crash, an outage, or an incident. It begins silently in the very first conversations, in the way requirements are framed, the way ambiguity is tolerated, and in the way risk is postponed. When a team starts building without a clearly defined perimeter, without constraint-driven architecture decisions, without a declared source of truth, and without maintenance planning, the failure is already present, only not yet visible. What you later call a back-end failure is simply the delayed exposure of a mistake that was already written into the project's logic. You can recognize this kind of failure before a single line of code is shipped, just by listening to how people talk about the system. If stakeholders are debating features while engineers are already implementing, there is missequencing. If the business cannot articulate why the system exists, but engineering is already discussing how to build it, the order of reasoning is inverted. If someone says we can add that later, it means the scope is not closed, which means the schedule is imaginary. These linguistic signals are not noise, they are diagnostics. A simple but illustrative example.